Welcome back, geology fans. How do we recognize a metamorphic rock as opposed to other rock types? Sedimentary rocks are made of pieces of other rock, tend to occur in layers, have fossils, or are monomineralic without being too recrystallized. This helps us distinguish the monomineralic metamorphic rocks, which are recrystallized. We said igneous rocks are usually a bit denser, having their crystals tightly packed together, but these minerals are not lined up. There is no fabric to the rock. This helps distinguish metamorphic rocks that do have rod and or plate-shaped minerals that lined up, giving the rock a fabric we call foliation. So the metamorphic rocks either have no foliation but look highly recrystallized, or they do have a foliated fabric. To my eyes, recrystallized rock has what I call a sugary texture, in that it looks like crystallized granular sugar. Today we will look at these sugary, non-foliated rocks that don't have rod or plate-shaped minerals lined up. We know that any mineral with one direction of cleavage will make plate-shaped minerals, and those with two cleavage planes make rods, or a mineral can simply grow into plate or rod shapes. Micas, amphiboles, and pyroxenes will all line up and cause foliation in a metamorphic rock, but we want to find the minerals that don't line up. Generally, these have three or more directions of cleavage or no cleavage at all. There are two principal minerals that are both common and fit this non-foliating blocky shape: quartz and calcite. But what are the chances you're going to have a rock made almost completely of quartz or calcite? Well, pretty good, actually, as quartz is one of the most durable minerals around and thus the main component of mature sands you might find at the beach. Such a sandstone can be taken down into the earth, heated and pressured, and turned from a sandstone into a non-foliated metamorphic rock called quartzite. Meanwhile, calcite is the main component of limestones, and the purest limestone is only calcite, which is a mineral stable at all but the highest pressures. The result is a rock called marble, and such pure calcite marbles have very little to tell us about the exact pressure and temperature the marble experienced. No distinct mineralogical changes occur to tell us about special conditions, and the main changes are recrystallization and grain growth, resulting in this sugary texture. But most limestones aren't pure, and in a slightly dirty limestone we are most likely to see quartz and clays, usually from clastic deposition, and maybe some organic carbon. With metamorphism, the organic carbon turns into graphite, and there might be some iron and sulfur to turn to pyrite as well. But we focus on the more active phases involved and find one of the most important reactions to be this conversion of calcite and quartz to the calcium silicate wollastonite and good old CO2. I count up 4 phases involved in the reactants and products, but only 3 components: CaO, SiO2, and CO2. So using the phase rule, we can have only 1 degree of freedom. In other words, all 4 phases can coexist only on a univariate curve of a pressure-temperature diagram. You have to be at a specific temperature for any pressure to get all 4 phases, which allows us a bit more detail in determining the metamorphic conditions our dirty limestone achieved. But let's focus on the CO2 phase in this equation. At metamorphic pressures, CO2 acts the same as H2O, as a supercritical fluid, which we defined 2 episodes back and you can conceptualize as a liquid under tremendous pressure. The CO2 in this state is perfectly miscible with H2O, that is, they mix together into a solution. We could have some water already present and add another component, but no new phases. So with some water present, we get 2 degrees of freedom. Clearly, fluids become very important in these carbonate rock reactions. So we have pressure and temperature as always as possible variables, but with a miscible fluid we get yet another, the composition of the fluid. The fraction of CO2 is equal to the number of moles of CO2 divided by the number of moles of CO2 plus the number of moles of H2O, total fluid. Let me introduce you to another type of graph we might use in metamorphic rocks. This is a temperature fraction of CO2 plot for our previous calcite and quartz to wollastonite and CO2 formula. We said if we have water present, there are 2 degrees of freedom, so I can choose any condition of pressure and temperature, and there will be a definite fraction of CO2 at which the formula transition takes place. Or I can choose a fraction of CO2 level in the fluid and a pressure and know exactly what temperature this reaction will take place at. Now let's complicate this a little more and assume our carbonate rock is not pure limestone, but a dolomite, in which magnesium has replaced some of the calcium in the crystal lattice. Suddenly the number of mineral species we can form increases, as there are many more magnesium-calcium silicate forms to change into, with the main forms being talc, tremolite, a variety of magnesium-rich amphibole, and diopside, a similarly magnesium-rich pyroxene. If we take dolomite down into the metamorphic world of Hades, it will first form talc if the right conditions are present, which is not always the case. But as we progress into the earth, we always see tremolite, the amphibole version, next in line, followed by diopside, or possibly forsterite, the magnesium-rich olivine member. With a variety of mineral forms, we can hone in on the metamorphic conditions much better than a pure calcite limestone. Just so you get an appreciation of the component diagrams we discussed previously, note that it is easy to plot a carbonate system on a tertiary component diagram with CaO, SiO2, and MgO at the points. Let's start with all the minerals that could possibly result from a dolomite. It's quite a messy zoo of forms, but now we use these diagrams properly and assign a given temperature and pressure condition. We start with the original sedimentary carbonate rock made mostly of dolomite, calcite, and quartz. With mild metamorphism, we see the dolomite quartz tie line get replaced with a talc calcite tie line by the following reaction. As we progress through higher and higher levels of metamorphism, our compositional diagram changes as so. Tremolite appears in the middle of the triangle of quartz, talc, and calcite because it is made from those mineral phases through this formula. And on the metamorphism of dolomite goes as diopside and forsterite appear finally. Quartz in a pure sandstone is like calcite and not telling us much about conditions as it metamorphoses, as quartz, with nothing else to react with, is extremely stable across the common metamorphic conditions. Again, we see recrystallization and mineral grain growth to get another sugary textured rock called quartzite. It may not be possible to tell quartzite from marble just looking at them, but as each are dominantly made of a single mineral, quartz and calcite respectively, we can simply use the physical property of these minerals to distinguish quartzite and marble. Quartzite will scratch glass, but not effervesce, being made of quartz, while calcite won't scratch glass and will effervesce, being made of calcite. Other metamorphic rocks which might be non-foliated include some types of baked zone hornfells, novaculite, or lapis lazuli, and hydrothermal alterations can lead to their own metamorphism. But the original chemistry of these altered zones make them a bit more complex to examine here chemically. Though marble and quartzite aren't very useful in telling metamorphic grades, the foliated metamorphic rocks are often associated with them and can be much more useful in finding the temperature and pressure conditions our rocks were subjected to, which we will examine in our next episode on the foliated metamorphic rocks, here on Earth Explorations.